want to look at variational encoders and what is the fundamental mechanism behind that. And then slowly we will progress towards GAN models in the next session. And then later on we will progress towards diffusion models. I'll try to keep it with a bit at higher level, and then we can also go a bit deeper as intended later on. But I kind of realized yesterday I was quite bad at giving good examples. So today I added some of the examples so you could see the bigger picture of why we are looking at these kind of variational encoders. One of the popular example here is that is the use of variational autoencoders for predicting the molecules. As you can see in the figure, here you see that you have multiple different molecules, and then you can start predicting how they start looking like. So, which means it has a bit broader implication, right? It's not only the computer science part that we are looking at, but it has a practical implications where it can be used for different use cases. And then another example, a popular example probably, is to also edit the expressions of face image. And now at this point of time, I'm only focusing on editing the expressions part. But in theory, you can use the variational autoencoders for multiple different applications. So which we'll be covering in some of the points in the later on. Okay, so what is a variation encoder, autoencoder? Take any kind of high dimensional data, which is typically an image, text, or any of the high dimensional data that can be represented in a small space. So that is the idea of latent space, right? So we want to go from a image which is 1 megapixel to something that is very, very little, as little as 32 bits encoding, right? So still this 32-bit encoding should contain high enough data, rich enough data, so that you can decode it back again. So there is a part of encoding, and then there is the latent space that comes in between, and then you want to go back to the final encoding, final output image. And then the whole goal of this variational autoencoders, or in the case of the latent models, turns down to this simple probabilistic problem, which is probability of x, which is the integral of probability of x given z and the probability of z across all the distinct across all the different discrete intervals, right? Now, we also, those of you who have also done this mathematical courses before, you know that some of these integrals are very intractable, which means it's very difficult to come to a solution. That's why we go for variational inference. I'll talk a bit about that variational inference in a short while. But remember, in the case of the VAE architecture, you have three components. One is the encoder component, which is dealing with some probability, and then there is a decoder component, which is again dealing with another probability. And the assumption here is that everything follows the Gaussian distribution, right? So we start with the real world observation, thinking that it's all Gaussian. And again, don't get confused with all the terminology that I'm using. I'm going to introduce each of the terminology independently now. So a typical architecture for any kind of variational autoencoder can be depicted here. So this is a picture I was looking for yesterday, and then I found a very nice picture. And this kind of summarizes the whole story behind the variational encoders, right? So, and this is and again, autoencoders also work in the very similar domain. You have an image here, you have an image here, and then you use whatever is your favorite network to encode the latent space, be it ResNet, be it AlexNet, whatever you would like. And then the intermediate representation that you're getting here is what is coming from discriminative models, right? So now what we are talking about is all the popular models that we discussed yesterday, like AlexNet, ResNet, and what Professor Nain was talking about, all those kind of simple models which can give you that representation, which is in the central part, right? And the idea of the variational autoencoders comes beyond this, where we take this latent code, which is typically very, very small representation from a very high dimensional image space, and then try to decode it back so that you get the actual input image here. It looks very ideal, right? So the point is that if you have a really good representation, you can reconstruct the whole image in a nice way. But what happens in the practical scenarios? It's not as easy as we think, right? So if you assume the data that is lying here, you look at the manifold here, it's not very simple, straightforward two-dimensional plots that we were looking at yesterday. So the data is very dense. The data can be distributed in different manifolds. And now to capture all of them into something very simplistic like here in the lower dimension, which has clear boundaries, and then to go back to the same domain is very, it's a inverse problem, right? It's a challenging problem. You can't simply go from one domain to another domain. So what if something goes wrong in this one? So let's assume that the point from this image mapped to this particular place here. So the point from this image mapped to this particular point here, and then if you are in a luxury situation, a lucky situation, and then what we could do is we could reconstruct this image back again, so the spaces kind of remain very intact, right? So then what happens in the other case is in the practical world is this one. So even if the points move slightly above and below, so then the reconstruction that you're going to get is this kind of funny cat video, a cat image, which looks like cat, but it's actually not a cat, right? And this is because of the space itself, the intermediate space that we have, which kind of maps the points to points. And what we want to do is that we want to get rid of this problem, and that's where the variational autoencoders come into picture. And here is the way one idea of modeling that one. So instead of looking at it as a point space, right? So if I have a text, let's take a simple example of text. So if I'm encoding one whole sentence in English to let's say to reconstruct it back again, and my whole sentence was, as we took the example in the morning, there was this summary of the Albert Einstein, right? And then the summary was quite short. Now if you want to reconstruct from the summary back to the original text that was given, it's a very complex problem, right? Because we are in different spaces, which is exactly the same problem that we have in the image space as well, also in the audio space, whatever the space you want to take into example. So one idea would be, how about we spread them in a specific region, in a specific probability distribution, so that we can reconstruct it back, right? And to do this, let's assume we have 1000 cat images, and if for each cat image we can assume that there is this probability distribution here, right? Now we are not talking about one point, we are talking about a bunch of points here. All these bunch of points will have some kind of properties, and the simplistic property is this mean that we were talking about yesterday. So any distribution, we take it as a Gaussian distribution, there is a mean, and then there is a variation, right? So you remember the statistical fundamentals that we were talking yesterday, that comes into picture here again. So as soon as I have this modeling from this mu1 and sigma1 for this particular kind of images, and I see there is also another kind of images here, for instance, in the second part here, and they have another mean and sigma, and they tend to be quite well separated, right? At least theoretically they are kind of separated now, right? But then there is also the practical problems, right? They are not as clean as the image that is shown here. They always tend to overlap with one another, and then you want to separate them and to reconstruct it very well. But now are we all on the same point that we understand the problem of reconstruction back again? So going from a high dimensional space to something that is very, very low dimension in terms of length, and then from that short length, we can go back to the origin length, right? So to draw another analogy, let's assume that you have your zip files. Most of you use your zip files, right? Zip or tar, whatever that is. So you compress the image, and then you reconstruct the image back. Or sorry, reconstruct the files back. You extract them back. But there we are using the either lossless or lossy compression, whatever we want to do, but we do not lose the information, right? But in this case, we lose the information. So the whole idea here comes down to the aspect of how do we retain that information to reconstruct it back again. To do that, we need to understand some small amount of probability here, not very complicated. This is something that everybody knows, more or less. If there is a model that is p of theta, p theta of x, then it explains the data x, right? And then you can say that it's nothing but it's a log likelihood probability of all the distribution across different instances, right? So it's nothing but we are going back to that Gaussian curve that we had yesterday, and then this is how we can represent it, right? And then as soon as we see that this formula is nothing but the log likelihood, and then if we are able to maximize that theta, then we are able to maximize the reconstruction, or the reconstruction error would be minimized. So now if you assume that here is how the log likelihood curve would look like. So you have this distribution, whatever that is, right? If it's a bunch of cat images, then you would get one distribution for that. Bunch of dog images, you would get something similar to that. And then you play with the distribution here to reconstruct the images back. Okay, now what would be the goal? If we have this background in the mind, then the goal is to have a model where data X can be represented as samples from the distribution. And now going back to the previous formula here, the goal becomes to maximize this probability, right? That is the simplistic goal. And then it looks very simple, but then I showed you that how complex it can be when it comes to the high dimensional space. The manifolds can vary, the distributions can vary, and the real world problems hit us hard. And that means that it becomes a complex problem. And now we want to model this slightly differently by taking the help of another auxiliary term, which is P of Z. So all we are doing is that if you have a P of X, so P of X is nothing but it's a probability of P of X given Z, and then P of Z itself, right? It's the Bayes theorem that we discussed yesterday, right? So what exactly happens in this case is that we start with something around like this, the probability P of X, and then we try to divide them into two. And here the goal is, given that Z, does it say something about X? Given the X, does it say something about Z, about X? So in the inverse way. And now within the VAE, what we are interested in learning a generative model that can learn to encode the data into the distribution, into the latent distribution. And now if we do that, it allows to sample the data from latent space to generate new data, right? So as long as I have come to a compact space, now I can pick and choose them, right? So if I have 10 values, let's say for the sake of example, let's start with a representation which can be let's assume that we have come to a simple latent representation, which is for a cat, it could be 1, 2, 0.5, and 0.3 for sample number 1. And then now I'm taking a 4 length encoding. And for the second one, I say 2, 1.2.4, and then I can say 3, 1.1.6. Let's say like this, right? So if I have 3 samples, now what I could do is as soon as I have this one, I could now pick and choose. I could say I want a cat with funny hair, so I can take this one, and this one, and maybe this one, right? So this should ideally give me a image from here to something like this, assuming that the encoder is very strong. And now the moment I pick this information, now I'll be able to generate a new image like this. Okay? So we are able to synthesize new set of images from here, right? So that is the goal of this one. So there comes this distribution, the probability distribution. How do we come to this one? And then from here, it's all about the freedom and flexibility that we get. Either we want to reconstruct the original images, or we can reconstruct new samples from this one. Okay. Okay, and then there are some also nice theories about this probabilistic graphical modeling and so on. But let's first try to understand the math behind it, and then we can try to go and play with the code. There is also the code available for this. I can share the link with you. It will take I think it will take around 15-20 minutes to run the code. You can do it in the evening time. Okay, so what is the problem now? Given there is a prior over a latent variable P of Z, what is the likelihood that we can end up with P of X given Z? And now this is a marginal likelihood. Forget about all those jargon terms, but just focus on the formula. The formula simply says that it's a simple combination of multiple probability, right? So it's P of x, and P of x itself is P of x given z with z over the distribution of uh, which is in discrete intervals d of z. And now within the variational inference, what we are going to do is we are going to approximate this first part, this one, and then to do this we need to maximize the evidence lower bound. So I'll come back to the evidence lower bound in a while, but remember the whole point of VAE now comes down to maximizing this one, or sorry, approximating this one for a given probability of given distribution probability. And then if you want to put it in a very simplistic manner, this is how an encoder would look like. So you have any of your encoder that is encoding this network. Let's assume that is an AlexNet or ResNet or whatever that you would want to prefer. And then you get this new space, latency, and then from there you decode it and then you reconstruct it, right? So I have this intermediate space, which is the latent that I am referring to as Z. Okay, so now I start looking at this complex problem, right? So there is this two terms that I have introduced. At this point of time, you probably will not, this will not make any sense. But let's take the math behind it, and then we'll be able to understand what is happening there. So let's start with the probability distribution all the way in the top. So we have P of x given z is this one, right? So the probability of x z is nothing but from here, how do I get related back to this original data space? And then simply by using the log transformation, I can say it as log of P of x is nothing but log of x comma z minus log of P of z given x. So I've just taken it to the other side, right? So if I derive that one, how would it be? It would be a very simple transformation I'm doing. I'm saying that, okay, P of x given z is equal to P of x and P of x given z, z given x. And now what am I interested in? I'm interested in modeling this part. So I take P of x equals P of x z divided by P of z x, right? Simple, simple relocation of the parameters. And then I can take the log here. So that becomes log of P of x. It's nothing but log of x z minus log of z given x. Nothing has changed. Everything remains as it is. Log of P of x of z. And then as soon as I have that, what I can do is I can take the expectation of that one, right? So now I have an expectation that is related to one distribution, and then I have an expectation related to the second term and the third term. Now this problem itself is a challenging problem, right? What we are trying to model, we are trying to model P of x, and then we are introducing something called as P of z, but neither do we have any information about P of x nor about P of z. It's a cycle problem, right? So you are trying to solve one thing, but you don't get the other one. Without getting this one, you can't solve this one, right? So you're continuously in a circle loop. So what can I do? So I can say that if I have this kind of a challenging situation, I'm going to introduce you two dummy variables, nothing but this one and this one. Look at that those two terms. Those are exactly the same terms, which is equal to 1, right? Or if you put them together, it's 0. So what I'm doing is I'm adding a 0 term there. By adding the 0 term, I can now separate the distributions in a nice manner. So what I'm saying is that, okay, this and this can cancel out, but let's keep that one for now and then just move it back into this equation. So now what happens is that this becomes log of x of z divided by q of z, and then on this side, this q of z divided by p of z. So what I'm trying to do is I'm trying to separate out the things that is not relevant for me and try to find out the things that are in my control. Everybody with me so far? At least from the mathematical part? Yeah? And then as soon as I have this one, I can start noticing some key characteristics. This is nothing but it's the L of Q, right? This one, this whole term. Now go back to the Bayesian formulation that we had before from yesterday. That exactly would be that. And now this part is nothing but the divergence between the two distributions. It's the distance between two distributions, right? Now, as soon as you have the distance between two distributions, you can say that it's a divergence factor, it's a distance factor. So I can compute it very easily because I would always have my distributions with me, and I can simply measure the distance between the distributions. So what we end up with is we end up with something like this, where we have one part which is talking about the expectation, and the second part which is talking about the distance between them. So now can you think about what should be done in this case? So as soon as we have the distance, what do we want? We want the distance to be maximized or minimized? It should be minimized or maximized?
Depends upon the context.
Depends on the context, it should be, right? And then so there is, the idea comes down to two terms. One is like one we want to minimize, the other one we want to maximize, right? So I was also looking for some nice examples for this. I came across one very nice example where they were talking about how can we relate it to real world. So the analogy was the first term can be your salary, and the second term is nothing but your bonus, right? So I kind of like the example, so everybody can relate to this. So there is this base minimum salary that we need to achieve, plus whatever comes on top of that, it can be bonus, right? It can be zero, but it can be a bonus. So which means that the distance on the second part can be zero, but it could also be more. So the more we have, the better the modeling becomes. Okay, so in that case, what we want is that we want to achieve this minimum criteria, and that's where the concept of evidence lower bound comes into picture. So now the only difference between this equation and this equation here is that, okay, we need to maximize this such that we get good term here minus whatever is coming up here, right? So no matter what you want to do, you want to have a better base salary, and bonus can be addition, right? So you don't really focus on bonus when you're signing up for a job. Now, in terms of the mathematical part, what we can say is that the first term is about reconstruction. How well am I coming back from a cat image to cat image, the actual cat image? And the second term is the regularization. So it's nothing but the same that we spoke about yesterday. We were talking about this lambda-based regularization, L2 regularization, which is exactly similar to that. And in this case, we want to push the distribution close to the probability of Z itself, right? So now we have broken the complex problem of this cycling to something simple, something that we can deal with, something we can actually implement. So in simple terms, the first part is the reconstruction loss, the second part is the regularization. And now within the ideas of VAE, what we want to do is this: we want to improve the reconstruction. At the same time, we want to enforce the latent structure space remains same, right? So what do I mean by that? So the first term is about reconstructing the cat itself, and the second part is to make sure that the cat has only 2 years, right? So it's very rare samples that we find maybe the cat has 3 years. It's never possible, maybe in very rare cases. So we want to enforce that semantic meaningfulness within the reconstructions. So we are taking care of two things. So if we are able to achieve this one, then we are able to achieve a very good variational autoencoder. Good. And then why do we actually look at the KL divergence, right? So KL divergence is one of the easiest to measure. It has its own merits, its own demerits. But in very simple terms, it can give you the measure of how much is the probability of Z given Q will vary from the given distribution of Q of Z, P of Z, sorry. And then it also encourages somehow the variables to stay close, right? The cat, all the representations, all the encoding of the cat should remain in same space. If you go back to the first picture that I was showing, we want to achieve this distributions which are kind of distinct, but at the same time similar classes come in the same structure, right? And then also as an added advantage, it also kind of prevents the overfitting of regularization so that it doesn't create all the time the same images. Right? We also want that, right? As a generative model, we want to achieve the cat images with some diversity. Sorry, with some diversity. Right? So those things are taken care of in this case. And now let's take a simple case of Gaussian noise, right? How does this scale divergence impact? So assume that you have a distribution which is having a normal distribution which is having a mu and sigma, and then the probability of anything occurring that one will lie between 0 and 1, right? And the KL divergence for this case is nothing but the mean of each term plus the standard deviation minus the log of that one minus 1. So this is nothing but a simple formulation. If you can work it out, you will end up with the same equation that you have there. Right? But the important point is not that. The important point is that when you look at the distributions, we will start looking at something like this. So here is my one distribution, here is my second distribution. So I can see that how much they are overlapping, how close they are. Right? And K divergence very nicely captures the relationship between them. If they are very different, then it will be very high. If they are very little, so they will come very closer. And then comes the second part, right? So I gave you the example of picking and choosing 1, 3, 4, and 5, and so on. It's very nice when you have small toy examples, but in the real world, what happens is like we are dealing with this kind of space which is very complex. So you cannot go from all the way, jump from Z0 to something Z1 without having some intermediate steps. So you will always interpolate between the points, right? So you cannot jump from A to B without having this intermediate A1, A2, A3, A4, and so on. So this is the whole idea of this VAE. And then when it comes to extensions, of course, there are a lot of challenges with the standard VAEs. So then there is other kind of VAEs. For instance, you have this discrete latent variables, which is VQ vector quantized. And then you have info VAE, which is based on mutual information theory. Now, the whole idea is that how do we deal with these distributions, right? So there you can plug in any kind of nice mathematical formulations that can help you achieve this one. So just to take this the divergence one more time again. So what is the divergence here? Is that it comes down to this whole formula. So the formula that we started with, it was this formula. P of x is there, Q of x is there, and then P of x is there. So if you put all of them together, you are trying to measure the distribution. Yeah.
Finding the KL divergence between P and Q, should it not be the same if I find the KL divergence between Q and P?
Yes.
If I have a log
No.
P by Q.
That's a very interesting point. So many of this distance measures that we use, for instance, Euclidean distance, is symmetric, which means distance from here to the place you are sitting is exactly the distance from the place you are sitting to me, right? In the case of KL divergence, it's asymmetric. So A to B is not the same distance as B to A. That's
in what sense then is it measuring the distance?
It's measuring with respect to the means.
With respect to the means.
With respect to the means, but it's not a symmetric distance, right? Because your distribution here in this case it's a nice distribution which looks very nice, but in real world it's not like this, right? So the distribution can be very skewed. Right? So that is a very good point. So in fact I think I have a remark somewhere later, but it's asymmetric. Okay, so then going back to the architecture itself, now you can see that we have input and then we have an encoder and then we come to the latent space Z and then everything further on is nothing but reconstructing the image again. So now you see that there is a small notation change which is saying that input is X and the output is X hat because we are not interested in recreating just X and X as it is, right? Because we want to synthesize new samples. Now, what is trainable in this case? So the parameters that are trainable is this encoder part, which is typically a discriminator model, and then you have the decoder, which is here. Right? So both of them are trainable, and then in this case, we make the loss a bit more complicated. As I told you in the beginning itself, there are two parts. One is the reconstruction part, and the second one is the distribution difference part, which is scale divergence part. And of course, there is a problem. As much as we can say that it's quite easy, it's not straight away. So what people do is there is a trick called as reparameterization trick, which allows us to do a lot of nice things, including the back propagation of stochastic sampling. Oh, sorry, back propagation of gradients. So if you assume this any z latent space, you have this mean, and then you have the variance. That is nothing new. And then along with the variance, now they introduce something called as epsilon here. Okay? It's again nothing but sometimes you might end up with sigma which is close to zero, and then you're going to continuously reconstruct the same sample over and again, which defeats the whole purpose of VAE, right? So how do we deal with this? By introducing some subtle noise, which is epsilon noise. And by doing this, we can now backpropagate all the gradients using the stochastic sampling. So yesterday, I remember we were solving the problem in the last session where there was a small epsilon factor added into this so that we could backpropagate the gradients, right? Which is exactly the same thing here. So nothing new. And then there is also this differentiability, which is somehow guaranteed because of the introduction of the epsilon. So what does this lead to? It leads to the case where we have this q of z of z given x, and then the z is now changed from mu plus sigma to mu plus sigma times epsilon. And this kind of now solves the problem that we can already relate from yesterday. The problem of backpropagation can be solved. Now the whole pipeline becomes slightly different. So we initially started with mu plus sigma. Now the only thing that is changing here is that mu plus sigma times e, and then rest of the other things remain the same. Okay, here's some idea at the overall high level, the idea of what is variational encoder, what is the latent space, and how we are reconstructing it. Okay, and of course when you're trying to implement it, you will come across some small issues that you can solve. I'll show you the example of how they deal with this the epsilon part in the code. Okay, and then the loss itself is also very interesting aspect, right? How do we solve this one? So there are two distributions. Then if there are two distributions, then it's not as easy as we think. They are not very distinct. They are not very how do you say well separated. So then we go back to using the concept of this Monte Carlo sampling. And again, I think most of the modern works in the VAE are a bit more sophisticated. So I'll give you some examples of that. But in the original version, it was the Monte Carlo sampling. So now putting everything back in one figure, you can see that this is how the whole pipeline works like. So you go from the encoder space to latent space using the KL divergence, and then putting together the reconstruction loss, you backpropagate it all the way to the input itself. Gives an idea? So which means that we are training both encoder and the decoder at the same time. Yeah? So it kind of takes care of reconstruction fidelity, and then also it enforces the semantic meaningfulness intact. Okay, in the case of a simple Gaussian encoder, again everything remains the same. Now the if you want to take it detailed, now you can say that q of this function is nothing but a normal function of a normal distribution of z given x, the mu of x and the sigma of x, and then you have the decoder which is exactly doing the same thing. Now it takes mu of z, not mu of x, and then we want to come back to this space, right? And the prior is that the assumption is that okay, everything follows normal Gaussian distribution, and then we plug the same formula that we had before, just adapting it to this particular context, right? So the base formula, which is having this the loss function, is not changing at all, right? Okay. Some benefits is that this is built upon well-founded theories of probability, right? So you're always guaranteed to get some solutions. It's not completely random. It's not completely stochastic, and it also means that you have a continuous latent space. So once you come up to the encoder, which is able to generate this latent space, then it's guaranteed to have some continuity in the space itself. And then as an added advantage, now we can say that, okay, now I can interpolate between them, right? So we created a new face image by picking up random samples here and there. That was one example. And then on top of that, I could also separate the latent space. So I could say that, okay, if these are the particular points that say that this is a cat, then I know that how can I characterize a cat from that one, right? So now you can also take it for different examples. Maybe some of you might be working on face recognition, and you are very interested in isolating all the pictures of females versus all the pictures of male. Now, as long as you can come to a very good latent space, you can separate them out. So what does that lead to? That would also mean that the moment you are separated, isolated, disentangled this latent space, you can change the identity of that person. You can make a person appear male to female, right? And there are also practical applications that we will talk about later, but you have an idea now how it can be used in real world. But then these are the benefits, but then there are also some limitations, right? So the limitations are very often they tend to come up with this blurry reconstruction. So the reconstruction might be completely out of the, yeah, it can be pixelated, for instance. And then one way to deal with that is that, okay, you can try to encode it, but how many combinations of blur can you encode it, right? So you cannot diversify the latency so much, and there is some inherent problem.
In starting there will be two endpoints, and
Right.
you cannot go beyond that endpoints.
Exactly. So you're
Decoders, you have to have that.
right. So you need to have this one-to-one mapping between the encoder and the decoder, right? Because if you remember from this picture here, we see that it's a complete cycle here, right? So even though you encode one blurry picture, but that doesn't guarantee you the reconstruction on the other side. Okay, so then comes the concepts of diffusion, which we'll talk about later. But at this point of time, you understand that although it's a very nice tool, there are some limited problems, some set of problems in this case. And then there is this other problem, right, which is called posterior collapse in powerful decoders, which means that you have a very powerful encoder which can encode every single information to a very nice unique latent space. And then if you are trying to decode it, so it can lead to the same sample over and over again, right? So which means that although I'm interested in creating the images of all of your faces, it might end up that it will always create the image of my pal, right? And this is not an unusual problem. This is a common problem that happens in many of the architectures. So how do we deal with this one? So then comes this idea of this beta disentanglement, which is again something like this. We have a new term that we introduced that comes over here. Now, just make an analogy between what we had yesterday. We had this lambda as a regularization parameter, which could actually help us to stabilize the loss functions, right? So now in this case, what we are trying to introduce is we are trying to introduce, in addition to the reparameterization, we are introducing something called as beta, which can help us in disentanglement. So then everything that we had from the part one, the formulation here, it still remains the same, except the fact that the KL divergence part is now supported by beta. So
So you will add one extra point to that.
one extra point, yeah. So this is nothing but it can be a small number, right? It can be a 0.1, 0.2, 0.3, whatever it is. So typically you add more beta greater than 1 so that it regularizes. And again, remember, all these things are nice, simple mathematical tricks, right? So the base theory remains still the same. So you have the reconstruction part, and then you have the KL divergence part. So one to take care of reconstruction, the other to take care of the semantic meanings. Okay, and then there is this other problem also, right? One thing is I solved this problem of the disentanglement, but then can I also make use of that in some sense? So if I know that I'm sending all the images of female and all the images of male, is there any way that I could also encode that information into the latent vector? Any ideas on how we can do that?
To get some assumptions there for. to add that parameters of assumptions.
We add that parameters of assumption it as a label. So all the images now that are going into the images, along with the images, I add metadata. Right? Example, let's take this digits, right? So the one that we are digits 0 to 9. So that means 10 possible digits. Instead of sending one channel, I'm sending 10 channels where the first corresponding to that particular image number or the digit number, right? So you are giving one additional space. Now for any digit that is represented as on 1, I'm going to send like this. The original image, this one remains as it is, plus I activate this person. Gives an idea? Or let's make nothing but image plus 0, 0, 0, 1, 2, 3, 4, 5. There's nothing. Now, if you want to do it as male and female, you have two. A binary vector, you say 0, 1. For maybe you write it as 1 and 0. So this is what's inside. And the moment we do that, we can also use the same decoder part. Right? So what is stopping me from not making use of it? Then I'm coming down to this point which is called as conditional VAE, where the condition now gives an idea, right? So now I have same base architecture which I'm keeping as it is, except that I'm making use of the labels at this point of time. So that is this condition. Example, if you are encoding the chest images for COVID, is that you have unlimited samples of chest images in COVID, yes, and then you have very limited samples of images, and try to encode it, then I'll be able to also transfer that one to the new set of images or generate new set of chest images with COVID symptoms. So all I'm doing is not, I'm keeping the base architecture as it is, dumping in the label, and the label is very easy to deal with, number of labels you want. Okay, so that is kind of the sum. Simply take some examples. So where do we use this one? We use it since 2014 onwards, I suppose. There are a number of new architectures that have come. And then the moment you can understand how the distribution looks, which is completely different, right? So what does that mean? That means that I will be able to separate out anomaly in the distribution. Let's take the example of spam and ham yesterday. Then anything that is beyond those kind of images, if there is a marketing image which is genuine, not a spam, then we can say that, okay, this is an anomaly compared to what we have seen before, right? Same thing happens. A particular person is able to is using the, and then suddenly there is a transaction in, let's say, South Africa, then I not belong to these classes. Okay, so those are some of the examples. Or the bigger use case of this one is representation learning. So here you have let's assume data into small chunks of representative. By doing this one, so we are able to say that, okay, the length of the vector for a very short vector which was length of 4, but if you are able to, then the more you compress, the better you can store the data. Still informative, highly informative. Okay, so let's see some of the things that we kind of understood today. So let's take a simple. Any answers for this one? Are we thinking about the reconstruction accuracy, or thinking about only the KL divergence, or somehow coming up to the point where we can at least give a low? If you have followed the topic. Now, when we are here, I think it's also a good time to just take a bit of reflection on why do we have to go to GANs if we already know stable, but then it ends up with blurry samples. On the other case, GAN bases itself on adversarial training, which I'll come back to later, but then GAN is also giving you very high quality samples compared to GAN, right? But then the moment we say that it's generating high quality samples, it also means that it's very hard to train. And the hard to train comes from the fact that the first one is probabilistic compared to VAEs. Parameters will be very high because you are talking about two networks. One is the discriminated network, one is the generator network, and then they have to interact with each other, right? Okay, so then particularly train network, what do we look at? So remember, we had the encoder, input image, encoder, latent space, decoder, and the output. To use, are we going to use the decoder, or are we going to use the encoder on the test data, or try to optimize Z for the best reconstruction, or just use a random noise X? Reasoning for that? How many of you think A? Can you give me any reason for that? Exactly. So what are we focusing on? We are autoencoders. So that means that we always sample from that particular part, right? So we use the decoder on that Z straight away. Okay. So the reason why we can't just use the noise is because there is that is completely meaningless. Question before I show some examples of this one. Again, remember there were two aspects. One is reconstruction. Okay, maybe you can simplify this. Assume it has a gap between two distributions. We know, and the posterior is something that we are creating, that's Z, right? So that somehow concludes this. But then, just for the sake of the base version will lead to a number of training instability. And then there is also this numerical stability with this sigma square, because sigma can lead to 0 if there is very down, but if your KL divergence is not under control, then your network is not going to be very stable. Okay, okay, and then maybe this I could stop here. I have getting something there. Okay, while I'm trying to show the demo part out there, is there any question so far? So here is the code that, and then there are some kind of installations here. But if you look at the central part, it's quite. Let's start with the dataset loading here. Zoom it up, but can you read this? Zoom it? No. I need to find out how to do.
Command and plus.
Command and plus? Oh, yes, that works. Okay, here. So it's again nothing new, right? So you have this encoder module, and the encoder module is quite simple. It has the linear, 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 and linear layer, 4 linear layers with 3 dimension, and then 1 leaky layer, and then that is what we are training. Again, remember this is a very simple crude example, right? And then you have the forward pass, which takes care of all these FC layers, and then you have, and then here, now you can see that we are computing the mean and the variance, right? Only 2 parameters. And then is the decoder module, which is the inverse of that, linear, 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 and then 1 leaky layer, and then there is the forward pass for that. And here we are using sigmoid, and this is the exact. So the original image and the reconstructed image. Right? Then we are defining the model, which is quite simple. Again, encoder and then decoder, and then they're all put together in this case. Yeah? So all this is all the code that you need for implementing the VAE. And then comes the training. Here you can define how many hidden layers, what is the dimension of the latent space. In this case, we are given a latent space dimension of, I think, 1024. Somewhere here. Batch size is this one, hidden dimension, latent dimension of 200. Okay. So from this 200 images, you can, once the model is completely well trained, so here you can see that the loss is going down. So this is from the pre-trained in the morning. So you see that it's 173. It goes all the way down to 100. At this point of time, the number of epochs are completed. And then I can already see the reconstruction of the images here. So it is able to generate the images for the index number 12. Okay, index number 12 is nothing but 10 samples per class, and then you are ending up with the sample number, the digit number 2, and then for another sample you get 8, and so on. Now, while I showed you that it's very simple network, right? Now you can already see the errors here. You see that? So can we make it out? Is it 6? Is it 0? Is it 8? It's 6, right? It's somewhat close to 6 visually, but actually the network is giving a confusing output. Okay. Good. I think again similar kind of problems can be seen here, right? Now this should have been an 8. It almost looks like a 2, right? Okay. So this code is not really very complicated. I'll share the code with you, so you can just try to run it on a collab if you don't have GPUs, and it should take less than 7 minutes to train the whole network, and to test it out you need a couple of minutes. Good. My part. should we continue or?
Yeah, we can stop there.
Yeah.
Then there is a small 10 minutes quiz.
Okay.
So we'll start after 5 minutes.
Okay. Okay. But in the meanwhile, is there anybody having questions? Some of the problems where you are working on where it could be used? Anything that you can relate to your own work? You can create any type of images, right? So, but what I'm thinking is that if you are already working on some specific problems, is there any way where you can think of applying this architecture?
Like we were using MRI images, but don't you think MRI images are very complicated? So will this model be able to create those images?
Yeah. There is no problem with the size of the images. Of course, you'll not be able to put the image that is 1 megapixel. You have to resize it, but then you can still, if you have the computational power, you can create it.
It will take time.
It will take.
MRI are having voxels. Right?
Yes.
Three-dimensional data. So then how do we?
No, two-dimensional.
So you can take the slices, right?
You have slices, but then how to create that whole voxel?
I think there should be some 3D VAE architectures.
One after another, we can put the one after another.
It's possible, but it will take a lot of computing. It will take a lot of computing.
So even if the computation is available, how to create that voxel? So how do we give a 3D input? That's my question.
I just Googled it, and then the first link. It takes the third dimension as well. At least I see a couple of implementations here. They do.
4 dimensions are also allowed to be given.
4, I don't know, but 3-dimensional. There is a paper here.
Or then 3 dimensions, one below the other.
Yeah,
Maybe one
yeah.
above.
So it's there is
Stacked up one above.
you can stack them up. Yeah, you can create like a volume.
The option which remains with that.
But when you stack their own complexities, sometimes it's like get overlaid upon each other or just
Yeah, this dimensionality.
Yeah.
Problem with the marking of the dimensions may be there, right?
they are not.